Thank you very much. Thank you for an invitation. I'm not sure I should thank you for forcing me to speak after such two wonderful lectures. It's a tough act to follow, but I'll try. So I will talk about the resolution of singularities. And the first lecture is just why does it work? I will not prove it. I will tell you why it works. And after this lecture, my goal is you'll know that it has to work in characteristic 0. And you'll wonder maybe why it doesn't work in characteristic P, but that's a different question. The theorem is Hironaka's. The joint work I'm talking about is with Belotto da Silva, Temkin and Wlodarczyk, especially the third lecture, so where foliations come in. There's also some joint work with Queck and Schober that I may or may not get to mention, most likely not. And I want to start by telling you how to blow up, because I don't think we blow up correctly. And this is, it's something that has been discovered many times over history. So David Rees introduced it, and then Miles Reed came upon it. Fulton McPherson, it comes up as a deformation to the normal cone. It's been around for several decades. David Cox, in a more general situation. Wlodarczyk introduced it in his treatment of factorization, and more recently with resolution. There's a treatment by Queck and Reed, which is still on it's still on David Reed's webpage. They promised to have it on the archive in January, and January has passed. It's 4 years old, or maybe 5. But we have been using it ever since. OK. Say again? Yeah, David Reed told me that this January that passed. Yeah, anyway. So if you want to pressure them, be my guest. So blow up using the deformation to the normal cone. And let's do a very explicit special case. Let's blow up this ideal on this variety, the affine space. Sometimes I forget that the field is C and call it K, but that's OK. And I'll write the following thing that is that David Rees wrote down many, many years ago. He called it the A transform. So this is this algebra over Y. You introduce an exceptional variable, S, and a transformed variable for each one of the generators of your ideal. And then you mod out by relations that you should find familiar. So the transform variables with the exceptional variables, the product is the original generators. I'll write B for the spectrum of this algebra. In Jarek's language, this is, a cobordism. This is the deformation to the normal cone. OK? I'll write V for the vertex of the deformation to the normal cone. It's the vanishing locus of the transformed variable. I'll call it the vertex. And I'll notice that there's a GM action on this, on the whole picture. Fixing V. How does it act? In order to act on a for GM to act, I need to basically grade this algebra. And I want the original variety to not have an action because I'm not given one. So, so you know what to do. You want to put weight 1 on xi prime, and this forces you to put weight minus 1 on s. So T so s has weight minus 1, and the xi have weight 1. I want to not write too crowded. Okay, so this gives you an action which fixes the locus V. And you notice that on B minus V, which is what Jare calls B plus, Jare calls this the cobordant blowup. It's a marvelous variety on which all computations, this is where you should do computations. So B minus V, B plus, has a free action. I think what I said is consistent with what you said. Okay? Yeah. Okay, so GM acts on this. And the wonderful thing is, if the xi are not all 0, then GM acts without fixed points, right? If x1 is not x1 prime, xi prime, if x1 prime is not 0, t times x is not the same as the x unless t equals 1. So the action is free. So you can look at the quotient B plus modulo GM. That's actually a variety. It's a variety that you know. It's the blowup of J on Y. Okay? This is the way you should write down the blowup. This is the place. Okay, so you do the computations here, and they restrict, of course, here. This is where you should compute. This is where you should compute the transform of a foliation, by the way, or a vector field. It's so much easier. It's shocking. Once you see this, you'll never go back. Sorry, Lorena. So, okay, so I'm telling you all this, and I have to, I mean, I owe you to show you that this is what you have learned from Hartshorne. And maybe I can convince you that. So let's say. So usually you look at charts where you can invert one of. So if not all of these are 0, then it's covered by charts that one of them is non-zero. Okay. So let's say xi is not 0, that locus has a GM slice, has a representative of each orbit, which is obtained by just taking xi equals 1. In other words, if I write bi where I invert the xi, so that's an open chart of B plus. Then bi modulo GM is isomorphic to just this locus, xi equals 1, because I don't need to take a quotient by anything at all. And once you plug in the equation xi equals 1, so xi prime, I apologize. Xi prime equals 1. Once I plug in xi prime equals 1, this means that xi equals s and xj equals xi xj prime. So these are the usual transformation rules that you're familiar with. That gives you so much trouble when you go from one chart to the other. Here you don't need to go from one chart to the other because there's just one chart. This is the chart. It's a GM chart rather than a birational chart. So if you allow yourself to work with group actions and everybody here is dynamical, then I think that's a pleasant prospect. Okay, I think I can throw this all the way up. Does this stop or do I? Yeah. Maybe I'll wait here and see how it goes. Okay, so there's a couple of things I want to do. One thing I want to do is to tell you what you do in general. This is a very specific example. I mean, we've all gone through EGA or Hartshorne. We want to know how to do things for an ideal. And the second thing is I want to do a picture. Oh, and the third thing is to generalize. I mean, the whole point is to generalize this. Okay, so the global point of view. The global picture is the following. And there's one change I want to do. This is J bar for a reason that you'll see later. So the global point of view, I'm going to confuse myself. Let's do the global point of view after the generalization. Okay? So first, I'll do the generalization, because that's what my notes tell me to do. So let's do a generalization. And the generalization, for a while, will look formal, and then I'll explain what it's about. I'll change the ideal J bar by this object where I put fractional powers on the xi. I'll tell you what this is in a minute. It's nothing mysterious. Okay? Still same affine space. I have to change things here because I want okay. Wi are integers, are positive integers bigger than 0. Could be 1. Thank you. So in order for everything else to work, I have to make this homogeneous. Okay, so how do I make this homogeneous? I'll keep the s with weight -1, but the xi prime, that's where the weight comes in, and that's why I left a little bit of space here and there. So the weight of xi prime is wi. The GM weight of the xi prime is wi. I still have, so I have an action. It preserves the locus where the xi prime vanish. I have an action, therefore, on B plus. And the action is no longer free now. Because if I set xi prime not equal to 0, the group of roots of unity of order wi still acts. Trivially on the xi, but non-trivially possibly on the others. Which means that in order to work with this, what I get is a quotient orbifold, and the correct thing to do is to work on the algebraic stack quotient of B plus modulo this action of Gn.
It's still t minus 1 times s?
So again?
It's still t minus 1 times s in the first factor?
Yeah, s is always of weight minus 1. So when s is non-zero, the action is free. It's just a product with Gm. When s is 0, something happens. And I'll draw a picture in a minute and explain this. OK? So I hope you don't mind. This is the one thing that maybe not all people in the audience are comfortable with. If you have problems, talk with Professor Beauville, who proved fantastic results on stacks. And so a long time ago. But anyway, so if you see a quotient, you work with the stack quotient. There's no reason to work any other way. There's still, inside B plus, there are still these open sets. And what you see in these open sets is that xi is not s, but s to the wi if you do these slices. So at any point, so on bi, the stabilizers are going to be the roots of, at most, the root included in the roots of unity of order wi. So it's still locally quotients by finite group actions, but only locally. Globally, it's a quotient by Gn. So this is the weighted blowup, I should say. This is the weighted blowup of this object. You might want to ask, what is J? If it's no longer an ideal, I have these fractions. Well, OK, so this is not unfamiliar to this audience. J is a monomial valuation. So it's just the valuation. So the valuation associated with J is the valuation that assigns to xi prime, to xi the value wi. OK? And when you have a regular sequence of parameters and you assign weights, then you have a monomial valuation by just formally expanding and taking minimum of non-zero terms. This enables me to actually continue with what I promised here, which is to tell you what is the global meaning of all this. So I told you what J bar is. At least locally, it's a monomial valuation. Globally, it's a Q ideal that locally looks like a monomial valuation. What is the Riesz algebra? This is it's a graded algebra after all. And what is Ra? It's just those functions whose valuation is at least A. So when you have a valuation, you have an algebra. And the algebra determines the valuation, and so you're happy. So it's in some sense, you could think of J bar as represented as the algebra, because they are equivalent. The notions determine each other. In general, V is the vanishing locus of R plus. R plus is just the positive part. It's the ideal generated by positive elements. Incidentally, when A is negative, this is just a structure sheaf. Okay, so in the case of the original, the unweighted case, this was I to the power A if A is positive, and O if A is negative. O is OY. It will always be O in the negative case, and it's important to me because if A is -1, there's I have OY in my degree -1. OY has a canonical generator. It's called 1. And that 1 is the S in this algebra. Okay, so it's a global thing. And of course, since you have a graded algebra, you have a GM action and everything. I wouldn't be done if as I promised, I didn't draw a picture. So no book in algebraic geometry should come without pictures. I might regret putting it here, but let's see. So let's try to analyze this and put, okay, so as I said, there's a canonical element S. In particular, this algebra contains the polynomial ring in S. In other words, B canonically maps to the affine line, right? So there's a canonical map from B to the affine line. Let's try to analyze this, and there's a special point here, 0, and let's take another point, maybe 1, it doesn't really matter. A point where S is not 0 is what I need, but set S equals 1. What happens when S equals 1 in the equation above? S equals 1, I get xi equals xi prime. So the fiber over S equals 1 is just the original variety y. Maybe I'll move it over here. And I'll put inside y the vanishing locus of the original variables. Okay? What happens when S equals 0? Okay, so I plug in S equals 0. This means that xi are 0. But xi prime are free to roam wherever they want. In other words, for each point on Z, on the locus where xi are 0, I get a full affine space. So this is precisely the normal bundle, or in a weighted case, the weighted normal bundle. I have colors. And here's a copy of Z inside it. And what is V? V is the vanishing locus of x1 prime through xk prime, which just means that, in particular, xi equals 0, but S is allowed to vary. So all the other xi beyond k are free to go. And okay, so what I get, so this is V, which is Z cross A1. There's one more thing that we want to have here before we add other stuff. we want to remember that there's a GM action. So how does GM act? Let's say at s equals 0, GM acts by expanding the xi with their relative weights. Along the vertex, xi prime are 0, so you only see the action on the s, which is with weight -1, so as t grows, s shrinks to the 0 locus, and the other orbits look like this. Okay? So this is the picture, which should be a familiar picture of the deformation to the normal cone of z inside y. In this case, it's a normal bundle because everything is smooth, with its projection, with its action, everything beautiful. And if you read Fulton's book and other works, you know that anything, many deep things about blowups are learned by studying the deformation to the normal cone. Okay, so in some sense, the deformation to the normal cone is the fundamental object. A blowup is an afterthought. I'm a bit exaggerating, but I'm the lecturer today, so allow me to exaggerate. Did I start this? Yeah. Okay. Time is flying. So I told you about blowups. Questions so far?
So the joist of the GM structure is not canonical, right? There is a joist involved.
So your question is, what is the structure underlying this construction? And the structure is a Riesz algebra or a evaluation, or a monomial evaluation. So there is something that you enter. So if you just have z, that's not enough. I agree. But weighted blowups appear repeatedly in our world. I mean, when we look at moduli spaces, they are there, and sometimes, and we ignore them to our detriment. So the weighted blowups are part of our life. Okay. I need to tell you about resolution of singularities. So what's resolution of singularities? I'll tell you about embedded resolution of singularities. I have a smooth variety and a singular subvariety. What's an embedded resolution? It's a proper birational map such that the proper transform is smooth. X prime being the proper transform. So there's one comment I want to say. I allow y prime and x prime to be stacks. Again, if you don't like it, you're in trouble because I'm the lecturer today, but I hope you allow me this transgression. I should, yeah. Okay, so this passed a bit faster. I want to tell you about invariants. Yeah. I think I need a full sideboard for that. So what's a singularity invariant? Let me know if my handwriting is deteriorating to the point that you cannot read it. That happens quite often. So a singularity invariant is a rule that given a situation like this, a singular variety and a smooth variety, gives you a function on the points of x to a set gamma so that gamma is well ordered. The function is upper semi-continuous in the Zariski topology. And it takes the minimum value if and only if P is smooth. That's not going to be enough for me. That's just a singularity invariant. I want to define for you a functorial singularity. So it's not just a rule, it's going to be a functor. Okay? And it's functorial not for all maps of varieties, but for smooth maps of varieties. So if y1 to y is smooth, and you define x1 is phi inverse of x, and I have a point p1 here which maps to p in x, then the invariants are the same. Invariant of x1 of p1 equals the invariant of x of p. So that's a functorial invariant. In particular, smooth maps include open embedding, so a functorial invariant is something that is locally defined. Smooth maps include isomorphisms, so a functorial invariant is canonical, namely it is functorial for isomorphisms. But it's more than that, okay? That's not quite enough. I want the invariant to be smooth. That is that the support of the maximum locus I want this to be smooth. So this is subvariety of x. I want it to be smooth. Is smooth. And I'll work only with smooth functorial singularity invariants. And again, this is not something, I didn't want to do that. This can stay here. I should say that the maximum value exists because I work with varieties, and if I have something upper semi-continuous, and in particular it's constructible, and varieties are Noetherian, so there is a maximum and blah, blah, blah. And the maximum locus is closed because it's upper semi-continuous. Okay. This I don't want to erase. I can erase the global stuff. I'm going to state you can stop me and ask questions, by the way. This is allowed. Which one is the good one? No. Neither of them. Okay. I think it's a so I talked about invariants. Questions about invariants. So let's talk about a criterion.
I'm sorry. The last proposition. This plot you say is closed?
Yeah. The maximum locus is closed because the invariant is upper semi-continuous. The locus where something gets the maximum value is equal to the locus where it has at least that value, which is closed by upper semi-continuity. That's
What are you asking?
topology.
You are asking this maximal locus to be smooth.
The maximum, the support of I want the maximum locus to be smooth, that's all. Ask me this in a little bit. Note that I'm allowing myself to use the letter P for a point because I'm not working in characteristic P in this lecture.
That's why the resolution does not work.
Because I don't have what I need. So I'll tell you now what I need. Okay, so here's a lemma. So you should all have gotten an email with my notes. And also in my abstract, I say, this is just, the lecture is about one paragraph in a paper that Jarek put in our book. And this is it. This is the paragraph. So pay attention. So if I have J, so assume we have an invariant, a smooth functorial singularity invariant, and assume that I'm given an X, and assume that I have a center as in the beginning of my lecture, as in over there. And assume that that this pair of an invariant and a center speak to each other. First, the support of J is that maximum locus. For this particular X. And second, I look up, I have B, yeah, I'll write something. So the maximum invariant on X is equal to the maximum invariant of the cobordism of X. And the cobordism is defined using this center J. So if you want, you can insist on putting a J here. So I'll use an extra color. So suppose I have my variety X here, which includes Z. It will be, and I form Bx by applying this procedure to X itself. X is singular, but I can just, if you wish, I can just take the proper transform. I take so away from S equals 0, this is just a product with GM, and I take the closure. So this is Bx. It's the thing that lives inside B, which takes care of X. And what is this? This is the this is the normal cone of Z inside X, if you wish. The fiber here is the normal cone of of Z inside X. Okay, so that explains what condition 2 says. Condition 2 says I have Bx now sitting inside B. B is a smooth variety, Bx singular, and what condition 2 says is that the invariant is the same. The maximum invariant is the same on Bx. I don't see higher invariant. So these are the conditions of the lemma, and the conclusion of the lemma is then on the blow-up, the invariant dropped. Okay? That's just one paragraph. And okay, so let me draw. So what I want to do now, I want to draw conclusions from this, and I want to prove this lemma. And then I want to give you examples, and probably that will be the end of the first lecture. And okay.
So these invariants are not defined only for subsets of Y, but they are defined for all varieties, right?
Yes, yes. But for now, the lemma is just about this particular x. So what Pereira is telling me is that I should look at what this implies in general. So corollary. Is this what you wanted?
No, just important because the dx has different dimensions than x.
Yeah. So corollary, but the blow-up has the same dimension. Okay, so corollary, if let's call this A and B. A and B with 1 and 2 hold for all x for all varieties, then resolution of singularities hold. I think that's the main point that your comment brings. So what Pereira says is that I don't have it just for one x, I have it for all x. So let's take my x, I want to resolve its singularity. I found another x, namely the blow-up along J of x, whose maximal invariant is smaller. And there's nothing to stop me from continuing. This is inside the blow-up of Y along J. It's a smooth ambient space. I apply this again and again and again. The invariant will drop and drop and drop, but it's inside a well-ordered set. A descending sequence will stabilize. When does it stabilize? When I cannot apply this, and I cannot apply it, so I assume that x is singular. I cannot apply it when x is smooth. Okay? So that corollary is an easy outcome of the lemma. Here's a theorem. This is due to us with Temkin and Wlodarczyk. It says such exists in characteristic 0. So the criterion for resolving singularities holds in characteristic 0, and therefore you have resolution of singularities in characteristic 0 according to this. Okay? So we have a clear-cut criterion. Here's what I need. I need an invariant and a center, an invariant to be defined for any singular variety in a smooth variety, and a center associated to it that speak to each other in this sense. Then I'll have resolution of singularities. So this is why resolution of singularities in characteristic 0 works. This is why. This is not how. How is next time. Yes?
The role of the weights was a bit unclear to me. The role of the weights is a bit unclear to me. Because I really have many choices, right?
Yeah, so I'll have to define a center. In particular, I'll have to define the weights. The weights will be defined using the invariant, and you'll see. So my aim is to give you a couple of examples now. I have 15 minutes, and give you more complete arguments tomorrow. And in the third hour, I'll broaden the perspective and talk about questions of Callum and Lorena. But there I'm really a student, so I'll tell you what I learned from people like André. Okay, questions so far? I want to give you now a couple of examples that show you that this actually, where this actually works. Maybe one non-example as well. I'm out of good chalk, so my handwriting will deteriorate now. So stop me if you can't read. So the first example is X is the vanishing locus of this. It's a Whitney umbrella. It's the second picture I'm drawing to the. I think every geometry lecture should have a few pictures. So I already drew a picture, but okay. This is the Whitney umbrella. You look at the equation and you see that the least order that any variable that you choose appears is 2. So the invariant will start with 2, and the center will start not j bar, but j. I'll tell you the difference in a bit. We'll start with 2, x squared, because x appears in degree 2. And then when you ignore x, you see that y and z appear in degree 3. So I'll put 3 and 3, 1 for y and one for z. And you notice that this is not a center that I know how to blow up according to that rule. There's a formalism that enables you to do that directly, but since I gave you, I'm the lecturer, then I'll transform. So J bar is obtained by rescaling this valuation to make it of that type. So this valuation that is the valuation that gives x the value 1/2. I'm writing here the stuff of weight 1. So 1/2, 1/3, 1/3, that's rational. That's why I need to rescale in order to be able to blow up. So J bar is x to the 1/3. I rescale by power 6th. Or I multiply the valuation by 6. And this is the center that I have. And if you see there, you see that the transform that I need to do is I need to write x equals s cubed x prime, y equals s squared y prime, and z equals s squared z prime. Oh, 1/2, 1/2, 1/2. How did I do that? Thank you. So people are paying attention. Thank you, thank you. But x is, yeah. So now, so this is the, so no matter what this means, you just need to plug this in. So let's do that. And try to make sure that you can read this. So I'll plug in, and I have, so f, the original function x squared minus y squared z is s cubed x prime quantity squared minus s squared y prime squared s squared z prime, which is just s to the 6 times. This just tells me there's 10 minutes, so I think I'm okay. x prime squared minus y prime squared z prime. Okay, so I'll allow myself to ignore this because this is the exceptional variable. I'm allowed to remove the exceptional divisor as much as it appears. So this is the proper transform. And I claim that things have gotten better. Why have things gotten better? On the face of it, it looks like I'm cheating. Remember, I'm doing, so there's an important principle. I don't know if, do I still have resolution of singularities on the board somewhere? Resolution of singularities. So I required the map to be proper birational. So the one important thing that you learned is that if you have a singular subvariety, the one thing you are not allowed to do is this. You're not allowed to erase the bad points. But here I am. Because here I'm removing the locus where x prime, y prime, and z prime vanish identically, the yellow locus, because I replace it by the orange locus. I'm not cheating, okay? So x prime, y prime, z prime not equal to 0, 0, 0 means that, well, if x prime is non-zero, then this is smooth. If y prime is non-zero, it is also smooth. If z prime is non-zero, then it's a surface with self-intersection. The invariant of this, where z prime is a unit, is going to be 2 and 2 on that locus. And 2, 2 is no matter how you do it. So, of course, I didn't tell you how things are ordered and why they are upper semi-continuous, so on, and well ordered. But 2, 2 is certainly less than 2, 3, 3, which is the invariant we started with. So things got better, which is exactly what the lemma tells you. If I didn't, on B itself, if I didn't remove, of course I got the same invariant because it's the same equation. But when I remove V, I got a lower invariant. So I promised a non-example, and the non-example is take the same variety, but now do the blow-up that you learned that everybody keeps doing for some reason that I don't want to, well, it doesn't matter. I can erase the resolution of singularities now. Let's do the usual blow-up of this example. It gets worse with other examples, but I'll stick with this example. If I do the blow-up of this ideal, then I plug in x equals sx prime, y equals sy prime, and z equals sz prime. The transform, the result is s squared times x prime squared minus s times y prime squared z prime. So now so y appears in the grid 2. The invariant is 2 at the locus where all the variables vanish. The invariant is 2, 4, 4, 4, which is bigger than 2, 3, 3. So if you do the wrong blow-up, it won't work. This is a manifestation of the well-known fact that if you blow up the Whitney umbrella at the origin, if you do things naively, things don't get better, but there are examples where they get worse. I mean, if you replace the Whitney umbrella by Yarek's favorite example, then things get actually worse. So you really have to choose. The lemma is not automatic. You really have to choose a center that speaks to the invariant, an invariant that speaks to the center. My last example, and the end of my lecture, is this. I look at this equation, x to the 5 plus x cubed y cubed plus y to the 100. 100 is just a number bigger than 8. That's bigger or equal to 8. That's what I need. Okay, so I drew here the Newton polygon with respect to these variables of the equation, this plane curve equation. So this stands for x to the 5. This stands for x cubed y cubed. And y to the 100 is something there. And so what's the invariant? So 5 is the order of vanishing. So I'll have to start with 5. And I need to think about how to continue. And then you have to carefully tune your variables so that you continue right. But in this case, the variables are already chosen for you. X and y are good. And so you just project the Newton polygon from this point, and you see where it hits. And it hits at 7.5. So this is because the 100 is way above. And therefore, the center will be. And one thing that you notice here is that the entries of the invariant are not going to be integers. On the other hand, their denominators are bounded. So the denominator here is bounded by 5 minus 1, basically, is where the next one would lie. So order, in terms of order, lexicographically, the invariant will be order equivalent to sequences of integers. So it's well ordered. And so let's see what happens here. This is a J. And again, I need to rescale it so that it looks nice. And J bar is going to be, again, I rescale by, so this is 15 over 2. I rescale by dividing by 15. And J bar is x to the 1/3 y to the 1/2. And if I plug in x, so what's the equation? So your notes will have this as an exercise. And you can do it on your own, but I'll do it very quickly now. So x is s cubed x prime, y is s squared y prime. This equation is going to be s to the 15. The 15 is the number L that occurs in the notes. X prime to the 5 plus x prime cubed y prime cubed plus s to the power 185 times y prime to the 100. So the stuff that does not lie on the supporting hyperplane of the Newton polygon has a factor of s here. But if you look at if you look at the singularity, the invariant, so on B, the invariant is still the same because it's still order 5, and once you project, this term will still dominate. So it's still going to be 5, 7.5 on B. If you remove that locus, then the new invariant will be 3, 185, which is less than 5, 7.5. And indeed, the invariant drops, and everything works. So what I told you is that there's a lemma, and if the conditions of that lemma apply, then you have resolution. And I told you that the conditions hold in characteristic 0, and I'll prove that next time. Or I'll give most elements of the proof next time. And I still have, let's see, yeah, this is it. Time over.
So are there questions, remarks?
Can't be that I was this clear that nobody has a question.
Okay, in that case, let's thank the speaker again. Thank you very much.